Okay, everybody, let's take a look at Unit C for thin airfoil theory. Now, this unit, we are going to take a look at very fundamental method of airfoil analysis, something called thin airfoil theory. This is based on vortex panel method in Unit C3, but it's actually a simplified version of vortex panel method. So mathematically, it is going to be very simplified math. So you can actually spend some time develop your own MATLAB code or your own Excel spreadsheet-based analytical method, and those will be your project 2B. Okay, so let's take a look at the first page. Okay, so first page, let's begin with what is the thin airfoil? So let's just go here. So it's a good idea to begin with vortex panel. Which is project 2A. BPM. And then I'm going to compare this against thin airfoil theory. So it's actually very similar to each other, but one is simplified version. So vortex panel method is, of course, you're going to use vortex panel. So assume that each one of them is a straight panel. Okay. So here is a panel of vortex. And keep that in mind, each panel has its own circulation. Circulation is a function of surface. So you can either put the constant value of circulation for each panel, which is first order method, or you can linearly change the magnitude of circulation for each panel, which is called second order method, which we covered in Unit C3. Okay. So you're going to use the panels to represent your two-dimensional body, and then you're going to superimpose against incoming uniform flow E infinity. Okay? The result is you're going to simulate the flow over two-dimensional cross-section airfoil. Now, one thing you shouldn't forget is that this method is going to enforce the cutter condition. Cutter condition really means that this circulation at the trailing edge must be set equal to 0. Okay, so this is the cutter condition. So by having cutter condition, the flow on upper surface and flow over the lower surface depart smoothly at the trailing edge, avoiding circulation close up at the trailing edge. Okay. And then the condition is something called stagnation streamline condition. That means the surface created by this panel, upper surface and lower surface, both need to be a stagnation streamline. Okay. Then in order to make this upper and lower surface stagnation streamline, what are the magnitude of each panel's circulation? That is going to determine essentially pressure distribution over the surface, and then you are going to have CP plot. Okay. And once you have a CP plot, of course, you can determine lift coefficient out of pressure coefficient plot. So that's vortex panel method, which is the project 2A. Okay. Now, you can possibly develop your own vortex panel method code using MATLAB, but it is quite a bit of coding. It's not easy. So I basically introduced you the code I developed, and then I let you use it. Okay. So now we're moving to thin airfoil cell, which is unit C4. So thin airfoil cell, this is a project to be, you are going to actually develop your own code, either MATLAB or could be spreadsheet. So what is the thin airfoil? Okay. First of all, let's just take a look at, this is a cambered airfoil. So that means you have a mean camber line. Okay. Okay. So I'm going to basically completely ignore the thickness of this airfoil. So I'm going to represent this mean camber line only using vortex panel. So that means this kind of thing. So this is the mean camber line. Mean camber line is represented by a series of panels. Each one of them is straight panel. So you can use numbers of panels to represent curved line, which is called mean camber line. Okay. So this is the, again, circulation per panel is represented. So you're going to use the vortex panel to represent mean camber line. Okay. Can we still apply Coulter condition? Yes, we can. In other words, the panel that actually creates the trailing edge, you can still do Coulter condition. Which is circulation at the trailing edge is equal to 0. Same exact Coulter condition. So whatever the panel that actually have at the very end of this mean camber line, you can put the circulation equal to 0, which is Coulter condition. Then of course, you're going to superimpose this mean camber line against incoming uniform flow, E infinity. Then what is the result? Well, result is very thin airfoil, because quite frankly, I just completely ignore the thickness effect. Very thin airfoil. Very thin airfoil simulated within the free stream. Okay. The same thing actually happens. That means this is the mean camber line of this thin airfoil. So this mean camber line needs to be a stagnation streamline. Okay. So by comparing those two, it's kind of similar. One is simplified because we basically completely ignore the thickness. So we are going to take a look at if the mean camber line changes, how does the rift change? That's something you can find out using thin airfoil survey. Okay, so let's move on. So let's take a look at the first page here. Okay, So as you can see here, this is the thin airfoil, sorry. So this is the extremely thin airfoil, could be symmetric, could be cambered. This is a cambered thin airfoil. So you're going to pick up the mean camber line and then represent that by a series of vortex sheet with a magnitude of vortex distributed for each vortex sheet. Okay. So this is a very classical, something called Randles thin airfoil. Okay. So let's consider this. This is the Z and X. This is the mean camber line. So as you can see, you're going to represent mean camber line using series of vortex panels and then superimpose against incoming infinity. Then forcing this line becomes stagnation stream line. Okay. Now we are going to make a one-step simpler approach, which is called classical Randles method. So rather than representing mean camber line using panels, because that is going to make the mathematics very complicated. So we are going to choose the chord line. Okay, this is a chord line starting from leading edge to trailing edge. We are going to represent the chord line, which is a straight line, using panels. Okay. Then we are going to compute the velocity which is produced by presence of this vortex panel at the chord, which is W. This W is equal and opposite to the velocity, which is velocity's perpendicular component at each location. In other words, if you take a normal component of incoming B infinity at all locations, okay, so suppose if the velocity is incoming B infinity with an angle of attack, you have, for example, if you look at this panel, velocity is incoming. You have a, probably not here, it's not good. Let's take a look. This is incoming velocity, B infinity. This is going to be two different components. B infinity S, actually, so this and that. This is a B infinity S, and this is called B infinity N. This is the this is the not very good. This. Okay, how's that? So this is B infinity S, this is B infinity N. Okay. In order to have this mean camber line to be a stagnation streamline, this B infinity N, which is a component perpendicular to each panel, this must be cancelled against by the velocity induced, which is W prime S, which is equal and opposite to B infinity N. So that velocity on this line is always tangential to this line. That is essentially you are making mean camber line becoming stagnation streamline. That's what you're doing. Okay. So what you're trying to do is, mathematically speaking, you are going to do B infinity N plus W prime S must be equal to 0. So you are going to satisfy this condition at every single location of the panel, forcing mean camber line to be a stagnation stream. Okay. So essentially, you are going to solve this equation and trying to satisfy this condition at each one of those panels. So suppose if you use 100 panel to represent mean camber line, every single panel needs to satisfy this equation. That is going to determine the magnitude of each panel. And once it is determined, you're going to determine pressure coefficient, and then you can determine lift coefficient, and also moment coefficient also. Okay? So that's what it is. And then one of the simplifications here is once you place your vortex panel at the code, you are actually going to create this W around the location of the code. And then at each location of the code, the velocity developed here is approximately equal to the velocity W prime S in the same location of X because it's a thin airfoil. So that's the approximation that Randles employed. So let me just call this Randles classical thin airfoil. So this really means that approximation given as page 3. Page 3 basically says that W prime S is approximately equal to Wx. So this actually simplifies the mathematics quite a bit so that you can actually develop your own code by hand. Okay. So this is the thin airfoil approximation based. Okay? If the airfoil is effectively thin, you can say this. Okay. Alright, so let's move on to page 2. Okay, so page 2. So page 2, I'm going to spend some time trying to figure out the geometry here. So first of all, this is a cambered airfoil, so this is a mean camber line. Mean camber line is typically a curved path. And then this is the difference between code and mean camber line. It's called the camber. It looks like this is a maximum camber located probably at the half code. You can change the location of maximum camber back and forth. Okay, obviously that's the camber. So what we are trying to do here is page 2. Okay. We are going to think about arbitrary location P. Arbitrary location P here on the surface of mean camber. Okay. Then you are going to draw a straight line which is perpendicular to this local spot P, and then find out the crossing point of the vertical line, and then find out the spot here, and measuring the angle here. This angle is basically inverse tangent of slope of this camber line at the point P, which is dz dx. Put the minus sign on it. Think about this triangle. Okay. So this is this triangle. So this is dx. This is dz, that's right. So inverse tangent of minus dz dx gives you this angle. Okay. Now if you extend this line and then having the same exact angle projected here, okay? This is the same exact angle geometrically speaking. This is also inverse tangent of minus dz dx. This is the angle here, okay? This is alpha, by the way, angle of attack of incoming V infinity. This is the same as alpha. So what I'm trying to do is, what is the perpendicular component of this V infinity called V infinity n? Let's go back here. That's what I'm talking about here, this V infinity n. So how can we represent this V infinity n? Okay? So the note says, let me fix this. So the note says V infinity n. This is a V infinity sine theta. Okay. Alpha plus inverse tangent minus dz dx. Okay? This is a equation coming from geometry. Let's go back and take a look at it once again. The geometry-wise, this alpha plus this angle, which is inverse tangent minus dz dx, those two angles added together, V infinity sine of that angle is V infinity n. Okay, it's coming purely from geometry. Let's go back here. Okay. Then let's assume small angle. Small angle means that this theta is going to be very small. And the reason is this is sin airfoil. So small angle assumption sine theta is approximately equal to tangent theta and approximately equal to the angle itself. Okay. So we are going to simplify this equation using small angle assumption V infinity n is approximately equal to V infinity alpha minus dz dx. This is an important equation. So important thing about here is this dz dx. This is the slope of mean camber line. So this dz dx is how the mean camber line behaves. In other words, what is this curve? If you kind of think a little bit more, if this is a symmetric airfoil, dz dx is essentially zero. Okay? It's a straight line, so there's no slope. So that's the symmetric airfoil. So dz dx is non-zero means this is a cambered airfoil. Okay? So can we express the camber line, mean camber line, in terms of the mathematical function dz dx? Yes, we can. It's possible. So that's the very important fundamental idea of how thin airfoil theory works. So the point is being that I want to apply this equation. So we now know what this is. So let's figure out what this thing is. Okay. So this thing can be given by, this is a small tiny W developed by the presence of panel. Okay, so this is interesting. Not so easy concept, so let me try, okay? So this dw, actually, differential value of w here. This is a very, very important and then very fundamental concept in aerodynamics. This is called downwash. Meaning-wise, this is the velocities component in the downward direction relative to the incoming free stream. This actually happens behind the wing, 3D wing, and this downwash, the original term is coming from, let's take a look, previous page. This is the downwash, which is the downward direction of velocity generated by the presence of vortex panel at the core. Okay, so because of the presence of panel, you're going to create the small tiny dWs just about anywhere along the core. What is Ae301 C? Let's understand this Ae301 C. Let's move on to Tennessee. Okay. So this is coordinate x, which is essentially chord line. Leading edge is x equal to 0. Trailing edge is x equal to c. Okay. Ae301 C is also the coordinate, which is essentially the same as x. Why do we use x and Ae301 C? By the way, Ae301 C is the lowercase Greek of x. Ae301 C is, okay? We need two different definitions of the location. That's why. So Ae301 C is the location of the differential panel, which is dx C. So this much length of the panel generate the downwash of W at the location of X. So let's go back. This is Ae301 C. Location of dx C, which is differential panel that contributes to the generation of downwash W. Okay, let's go back to this picture once again. So this is actually coordinate location. Now what about this x? X is, again, the coordinate location of the downwash W, which is generated by this particular differential panel located at location Ae301 C. This is X. Location of W, which is generated by the presence of dx C. Okay. So this is not so easy concept, but where does this coming from? This is coming from something called Helmholtz vortex theory, which we're not going to cover that, but this is essentially fundamentally coming from somebody who found how much velocity is induced by the presence of the vortex panel. And then this is the downwash you can generate by the presence of this small tiny vortex panel at the location of Ae301 C. And then you can generate this much downwash at the location of X. Okay, let's understand properly here, which is kind of confusing. But it's very important to distinguish those two differences, X and Ae301 C. Those are both coordinate, but it's slightly different meaning. Okay. in order to have the overall total value of downwash W, you can integrate this one from leading edge to trailing edge. So let's do that. So what is the total W? This is a function of x. Okay, this is minus integrate from leading edge to trailing edge of that dW. Circulation gamma as a function of xc multiplied by dxc 2 pi x minus z. This is called the downwash equation. Okay? So, in order to enforce, okay, mean camber line to be stagnation streamline, of course, you need to set B infinity n plus W prime S, which is approximately equal to W as a function of x, must be equal to 0. Hence, you're going to get this equation, V infinity alpha minus dz dx minus integral from leading edge to trailing edge gamma as a function of xz dxz 2 pi x minus xz must be equal to 0. So this is the governing equation which you need to satisfy at every single panel for thin airfoil cell. So suppose if you have 100 panel to represent mean camber line, you come up with a 100 equation you need to simultaneously solve to satisfy what the gamma you should have for each panel in order to satisfy this equation. So essentially that's what you're doing. That's the solution of thin airfoil cell. Now there is good news. Good news means that you can analytically solve this equation, something called coordinate transformation technique. Okay. So this is called mathematical solution. By coordinate transformation. So this is a math technique, and this is not really, important. Well, it's important, but it's not the scope of this class anyway. So let me just give you the solution, okay? So we are going to transform x into variable xz. Let's transform variable xz to theta by using this equation. Xz is equal to chord length divided by 2 multiplied by 1 minus cosine theta. Okay, so this is the coordinate transformation equation from coordinate xz to coordinate theta. Okay, if that's true, if you take a differentiation of xz called dxz, dxz is, if you differentiate this one with respect to theta, this is going to be chord length divided by 2 sine theta d theta. Okay, so those two are very, very important coordinate transformation equations. And also another thing, let's transform x to theta 0, by using same exact equation, x equal to chord length divided by 2, 1 minus cosine theta 0. So we are going to coordinate transform. If so, okay, this equation is going to be coordinate transformed by using those transformation equations. Now the equation becomes this. B infinity alpha minus dz dx is equal to, not equal to, minus integral from leading edge to trailing edge. So this is going to be 1 over 2 pi, integral from 0 to pi, gamma. Now it's a function of theta, sine theta d theta, cosine theta minus cosine theta 0. Okay. So this is a transformed equation. So this equation, based on x and z, now is in terms of theta and theta 0. Why are we doing such a thing? Because we can integrate it mathematically to find out the solution of gamma. Okay? So, I don't know. Here is this one. Okay? So, the thin airfoil equation can be integrated to determine, actually not integrated, it's just solved, can be solved, can be mathematically solved. To obtain the solution. I am skipping some details. The reason why I'm skipping some details is this is not math class, this is engineering class. So I give you the solution. Solution is this. Gamma as a function theta is 2 times alpha. Sorry about that. Let's go back a few lines. Okay, so let's not skip too much math. So first, I want to show you a solution for the case of symmetric airfoil, okay? Symmetric airfoil really means that the dz dx is equal to 0. if the dz/dx equal to 0, that's the good thing. This is 0. And then just move up a little bit. This is also 0 if it's symmetric. So if it's a symmetric airfoil, the equation is B infinity times just alpha. Okay, so B infinity alpha minus 1 over 2 pi integral from 0 to pi gamma as a function of theta sine theta d theta divided by cosine theta minus cosine theta 0. So this is the equation for symmetric thin airfoil. Solution for this equation is this. Gamma as a function of theta is simply given 2 times alpha b infinity 1 plus cosine theta divided by sine theta. This is a very well-known symmetric thin airfoil solution. So we're going to use this, okay? So I'm skipping a few things. What am I skipping? I'm skipping from here to here. I'm completely skipping. I don't want to show you the details because this is not mathematics class. So let's not worry about how you get this from here. Let's not worry about it. If you're interested, it's a math question. We probably going to use this because we know this is a very well-known, famous symmetric thin airfoil mathematical solution. So we're going to pick up this result and then derive what does this result implement. What does this tell you about lift coefficient, moment coefficient, and other things. That's what we want to do. So right now we are in page 4, so let's move on to page 5, okay? So, this is called thin airfoil, actually symmetric, symmetric airfoil solution. So we are going to start from here. This is the solution. Gamma as a function of theta is 2 alpha b infinity 1 plus cos theta over sine theta. So we're going to start from this mathematical solution of symmetric thin airfoil. Okay? Alright. So, well, actually, before moving on to page 4, page 3. So we have page 3, okay. Let's move on to page 4 now. So before moving on to page 5 and page 4, let's take a look at one thing. So let's say this is the code. This is the leading edge. This is the location where your DXC is. This is a small tiny segment of the panel that actually create lift. Okay? Location is at XC. Now, we are going to understand what this picture really means. Okay. So let's find out. Let's find out. Small tiny dl the location xc. You take a differential element dxc. This is essentially vortex panel. Okay. And this dxc generates circulation. The gamma is essentially circulation as a function of xc multiplied by dxc. Okay. This lowercase gamma is the circulation per unit length. Okay. So this much circulation per unit length multiplied by this much small tiny length gets you the small tiny amount of circulation at the location xc. This circulation is created by this small tiny element dxc. Okay. This is circulation generated by this dxc. That's what you see. Let's take a look at this one. So this is a small tiny segment dxc. This is part of the vortex panel. This vortex panel comes with the magnitude gamma as a function of xc. And multiplied by this small tiny segment gets you the small tiny circulation developed by this panel segment. Okay? And then let's remember Kutajikovsky. Kutajikovsky's theorem says lift per unit span is rho b gamma, isn't it? Okay. So what is the small tiny dl generated by the small tiny d gamma? dl prime is rho b d gamma. Okay. So let's think another thing. So this small tiny dl multiplied by this much distance, which is xz, creates the moment around the leading edge. Right? This is the moment arm. This is the dl generated at the location xz. This one is generated by this segment of vortex panel, which creates leading edge moment. Small tiny leading edge moment. So that is essentially dm prime le, which is, by the way, this is a pitch down moment, so it's minus. Okay, so I'm going to put minus xz times dl prime, which is minus xz rho infinity b infinity d gamma. Okay, so moving on. So this actually tells you, so what is the leading edge moment developed per unit span? You're going to integrate this, right? So you're going to integrate from leading edge to trailing edge d mle prime, which is, of course, that equation. So you get minus rho infinity b infinity, there's a constant, goes outside of integral. So integral from leading edge to trailing edge, xz is the distance, multiplied by gamma as a function of xz, multiplied by dxz. So let's understand where does this equation come from, okay? Which is given in the note already, okay? So let's understand where does this equation come from. It's coming from this picture, okay? So let's move on to the next page, page 5. So page 5 gives you really simple equations. So let's derive each one of those simple equations, which is very, very important. Okay, let's take a look at it. So this is again symmetric thin airfoil equations. Very important. So I hope you watch this video. If you watch this video, you realize how important this derivation really is. So let's move on. Okay? I believe I emphasized enough. Stop. No, don't touch it. Okay, let's continue. Okay, so circulation gamma. Circulation gamma, this is the total circulation. Of course, this is integral from leading edge to trailing edge. Differential element of d gamma. Okay, so remember this d gamma, take a look at this. Okay, d gamma is coming from, this is the circulation as a function of xz multiplied by the actual length of the element that is creating circulation. So let's just move on here. This is going to be integral from 0 to c gamma as a function of xz dxz. Okay. Now, what you really want is you're going to do coordinate transform. Remember, let's use this equation. Coordinate transformation. Xz is equal to half code 1 minus cos theta. Dxz is half code sine theta d theta. So remember, those are the coordinate transformation equations. Okay? If you do a coordinate transformation equation applied, you're going to have this. Circulation is now not as a function of xz, it's a function of theta, right? So this is going to be half code integral from 0 to pi gamma as a function of theta sine theta d theta. Okay? Then, important thing is, you know what this is? It's coming from here. Okay? So this equation, boom, coming in. Therefore, gamma is half code integral from 0 to pi. Let's plug in gamma theta. So this is 2 times alpha b infinity multiplied by 1 plus cos theta divided by sine theta multiplied by sine theta d theta. Right? Obviously sine theta cancels. Then this is fairly simple. Integration from 0 to pi to alpha b infinity. This goes outside. 1 plus cosine theta d theta. If you integrate from 0 to pi, this is what you have. This is going to be 2 cancels. So this is alpha goes outside chord length b infinity. This is all goes outside of integral. Integral from 0 to pi. 1 plus cos theta d theta. Okay? So you can finish up this one. So gamma is equal to Okay. What is integral from 0 to pi 1 plus cosine theta d theta, which is interestingly pi. Okay? So, the answer here is pi alpha c b infinity. So, this is the circulation developed for a thin airfoil with the chord length c with angle of attack alpha, which is an amazingly simple equation. Okay. Now, once you know the circulation, next thing is, of course, you can determine lift coefficient because Kutajoukowski relates circulation to the lift. Okay. So next step is Kutajoukowski, right? Kutajoukowski theorem relates lift per unit span is rho v gamma. We know gamma. Okay. So let's plug in. So rho v gamma we know pi alpha chord length b infinity. Okay. Which is pi alpha c rho infinity b infinity squared. So this is a lift per unit span. From here, let's find out section lift coefficient. Which is CL. Obviously, L prime divided by Q infinity times C. L prime is pi alpha C rho infinity B infinity squared. Q infinity is 1/2 rho infinity B infinity squared. C is cold. Obviously, rho cancel, B infinity square cancel, chord lengths cancel. What do you have here? 2 pi alpha. Oh, wait a minute. Have you ever seen this? CL equal to 2 pi alpha. What is this 2 pi? This is called Ae0, which is lift curve slope. What is lift curve slope? Do you guys remember? I hope you guys remember. If you plot lift coefficient CL against alpha, this is a symmetric airfoil, so at the zero angle of attack you have a zero lift. This is the relationship between CL and alpha. This is the slope called A0. This equation tells you CL is equal to A0 alpha, which is essentially 2 pi alpha. A0 equal to 2 pi per radian. So you're proving that, hey, this is the equation we used already. It's coming from thin airfoil theory. Okay? So this is one of the interesting mathematical derivation of this very, very useful equation. We already used it quite a bit, which is coming from here. Okay? All right. So let's go back to here. So now we looked at, hey, this is CL is 2 pi alpha, then that means lift curve slope, dCL d alpha. This is the definition of this A0. It's 2 pi. Okay? Lift curve slope, this is A0. Right. Next step, let's find out how much moment is developed at leading edge, which is M prime LE. Well, this is obviously, this is minus integral from leading edge to trailing edge dM prime LE, in which we did it, which is minus integral from leading edge to trailing edge, xz times dL. Okay? Remember, so this is, if we plug in the previous equations, about dm prime le into this equation, minus rho b infinity integral from 0 to c xz times gamma as a function of xz times dxz. Once again, you're going to do transformation. Transform xz into theta, right? So xz is half code 1 minus cos theta, dxz is half code sin theta d theta. Okay, we are going to apply this coordinate transform, in which we are going to come up with if you go through this transformation, do the mass, we're going to have minus q infinity cos square pi alpha over 2. Okay, now, so then what is the section leading edge moment coefficient? Which is CM LE. Okay? So this is obviously M prime LE. Leading edge moment per unit span divided by Q infinity multiplied by cos square. Okay? Which is what? Minus Q infinity C square pi alpha over 2 divided by Q infinity C square. Oh. Obviously, this cancel, this cancel. This is going to be minus 1/2 pi alpha. Wait a minute. Remember, CL is 2 pi alpha, isn't it? So let's plug in this. CM leading edge is equal to, what is it? CL divided by 4, isn't it? So, moment coefficient at the leading edge of thin symmetric airfoil is whatever the section lift coefficient divided by 4 minus. So this is leading edge moment coefficient of the section. Okay? Now, recall, moments are all related. One of the relationship between leading edge moment and quote-unquote moment is that Cm quote-unquote is equal to Cm Le plus Cl divided by 4. This is a relationship. When did I do? I think I did it in early units. Unit A, I believe unit A5 when we derived center of pressure. You know, we discovered the relationship between leading edge and quote-unquote moment through lift coefficient, right? So we're gonna apply. Well, this is from, I believe, unit A5. Okay. So we're going to apply this equation to find out what is the quote-unquote moment coefficient. So obviously, Cm quote-unquote is CMLE, which is minus CL over 4 plus, oh wait, CL over 4, what's that? 0. Oh, okay. So, wait a minute. This implies a kind of interesting thing. So we are talking about the thin symmetric airfoil moment coefficient at quote-unquote is 0. This means two things. Therefore, for symmetric thin airfoil, quarter code is both. First of all, what is the location where the moment coefficient becomes 0? That's the center pressure, right? Moment is 0. Also, 0 and then 0 is constant. So this is aerodynamic center as well. Because moment is independent to alpha, which is constant. Constant against alpha. So this implies that symmetric airfoil quarter code is both center pressure and also aerodynamic center. This is actually called neutral point. Importantly, so this is a very, very important conclusion from symmetric airfoil analysis. Okay. All right. So move on to the next page and let's take a look at some examples. Those are very, very easy examples. So let's consider a symmetric thin airfoil, such as, good example is NACA 0006. This is a symmetric, maximum thickness at the quarter code is 6 of the quadrants. So let's just put this airfoil in 4 degrees alpha, and then let's calculate the following using symmetric airfoil center. Lift coefficient at 4 degrees. So 4 degrees need to be first of all converted to radian. So this is 0.06981 radian. Let's be careful, this equation is all radian because 2 pi is radian. Okay? So A, CL is equal to, of course, 2 pi alpha. So this is 2 pi times 0.0698 radians, which is equal to 0.4386. This is the lift coefficient at 4 degrees. Part B. What is the moment coefficient at the quarter code? It's 0, right? Alright, so let's move on to the next page and take a look at if this is really true. So next page. So this is NACA 0006 actual wind tunnel testing results. So CL at 4 degrees alpha here. Right here. 0.4. Okay. 0.4 versus 0.43686. About the same, but that one actually over-predicts. The reason is this is not really straight line. This is probably slightly curved path, so that's why the actual CL is lower than that 2 pi alpha, but it's not so far away. Number 2, quarter code moment coefficient, which is this. Oh, it's pretty much 0 and constant. How's that? Okay? So thin symmetric airfoil theory actually predicts CO and quarter-chord moment fairly well, right? As you can see. So that's the next page. So from NAC 0006 data, CL is 0.4 at 4 degrees angle of attack or alpha. CM quarter-chord is 0 and constant in the range between -8 to 8. So as long as your airfoil is not in the stall region, you can say those, which is fairly good, much against thin symmetric airfoil theory, right? Okay. So we can use this for preliminary design analysis, which is equation super simple. Okay. So now, this is the neo subject, which is part of your project 2B. So let's move on to the next page. Okay. So your project requires you to analyze the Cambered airfoil. Okay. So far we've been using Symmetric. What is the big difference between Symmetric and Cambered? This is a Symmetric. This is alpha versus CL. Slope is A0, which is 2 pi already. If you put the camber, assuming it's a positive camber, you're going to shift everything to the left. Then you are going to introduce alpha zero lift angle of attack. Typically small negative value of alpha to generate zero lift. However, this same A0 can be applied. Is that right? This is a Cambered airfoil. Okay. So Cambered thin airfoil requires, number one, what's alpha zero lift? And number two, what's CM quarter-chord, which is not the zero. Remember, if it's a symmetric airfoil, this is 0. If it's cambered, this is not 0. Okay. So let's take a look at page 8 of your note. So we are going to go back to the original thin airfoil theory equation. Remember, this is the original thin airfoil equation. 1/2 pi integral from leading edge to trailing edge, gamma as a function of xz multiplied by dxz, x minus xz is equal to v infinity alpha. That was symmetric. V infinity times alpha minus dz dx. Now this dz dx comes back in. This is x, this is z. This is 0, this is x equal to c. This is the mean camber line. Okay. So now mean camber line comes up with dz dx, which is not 0. So dz dx is a function of x. dz dx is essentially the slope of mean camber. Okay? So first of all, you have to represent this dz dx as a function of x, then you have to solve this equation. Okay? So here is the solution. Okay? Interestingly, we can still solve mathematically this equation by coordinate transformation. Remember, coordinate transformation is same exact coordinate transformation. Z is half code 1 minus cosine theta. dx is half code sine theta d theta. X is equal to half code 1 minus cosine theta 0. Okay? So we can still apply the same exact coordinate transformation equation. Then you can transform this equation. And then solution is gamma as a function of theta, which is equal to 2 times b infinity A0. A0 is a coefficient. 1 plus cosine theta divided by sine theta plus summation m equal to 1 to infinity am sine m theta. This is a solution, mathematical solution. Okay. Then we're going to do the same thing. Starting from this solution, you're going to find out solution of gamma as a function of theta, we can have the following. We can have the following, which is given here. First of all, CL is equal to 2 pi alpha plus alpha 0 left. Actually, no, minus. Yeah, minus. Alpha minus alpha 0. Yes, that's right. Which is essentially, oh, it makes sense. Alpha and CL. This is alpha 0 left. This is A0, 2 pi. 2 pi already. So this line is CL is equal to 2 pi alpha minus alpha 0 left. Goes. Sure. Then the question is alpha 0 left. What is it? Alpha 0 left can be given by minus 1 over pi integral from 0 to pi dz dx cosine theta 0 minus 1 d theta 0. So, how do you find this? You are going to find out dz dx as a function of theta. In other words, dz dx is essentially function of x. Then you are going to coordinate transform x into theta 0. and then multiply by cosine theta 0 minus 1, then integrate that from 0 to pi. Then you get alpha 0 delta. Okay? We're going to find out how to do it later. But we can fairly easily do this. And also another thing is Cm leading edge. Cm leading edge is minus, okay, Cm over 4 plus pi over 4, A1 minus A2. What is A1? What is A2? Let's find out right now. Cm quarter code, of course, is related against the leading edge moment. So this is pi over 4, A2 minus A1. So question is, what is A2, what's A1? A2 and A1 can be found. A2, actually, coefficients. Coefficients is this. Let's take a look. Coefficient A0, coefficient A1, A2, A3, A4, A5. But what you need is A1, A2 only. Okay. So coefficients. A0 is alpha minus 1 over pi integral from 0 to pi dz dx d theta 0. So this is the coefficient A0. Coefficient An, n equal to 1, 2, 3, to n, is equal to 2 divided by pi integral from 0 to pi dz dx cosine of n theta 0 d theta 0. So those are the coefficients A0, A1, A2, A3, but what you need is probably A2, A1, okay? So coefficient A2 is plugging n equal to 2. So this is cosine 2 theta 0 d theta 0. A1 is plugging n equal to 1, so 2 over pi dz dx cosine theta 0 d theta 0. Okay. So this is going to solve CL for a given alpha. This is going to give you quote-unquote moment coefficient for also given alpha. It is going to be very important information. This is going to actually give you information like this. So you can use the symmetric thin airfoil cylinder. This is one. You can use the Cambered thin airfoil cylinder. This is, by the way, symmetric. But for a given alpha, you can determine CL and moment coefficient of quote-unquote. So you can represent this and that using Cambered airfoil. Okay. If it's symmetric, of course, quote-unquote moment 0. And this is 2 for alpha. If it's cambered, it's going to be not the constant value. And this whole thing is shifted. But you can find that nonsense. Okay, that's your project 2D. Okay. Alright, so let's finish up this unit by concluding. Let's just take a look at a little bit about the real flow field. We've been talking about ideal flow, vortex panel method, and also thin airfoil theory, both based on ideal flow. Of course, we can add viscosity on top of those models to represent a little bit more realistic type of flow. But if you look at such as wind tunnel testing, for example, it's a real flow. Okay? So what is the big difference between thin airfoil versus thick airfoil? It is going to behave differently. Okay? So first, let's take a look at the thin airfoil. This is a relatively thin airfoil, even though this is 12% of the code, NACA 4412. This is a Cambered thin airfoil. Obviously, if you place it at 0 alpha, you're going to generate already this much CL. If you pitch up 2 degrees, you're going to generate 0.35 CL. Pitch up 5 degrees. You produce 0.55, 0.6, okay. Then if you pitch up 10 degrees, 1.2. 15 degrees, you are about to stall, and then this is the maximum CL lift coefficient, 1.6. Okay. So this is right before the stall, and then if you pitch up a little bit more, but it stalls out. It's right here. So let's just take a look at this picture and that picture. This is a pre-stall, this is post-stall. And then one of the problems of thin airfoil, realistically speaking, if you choose the thin airfoil for your design airplane, this is what happens. Thin airfoil begins to separate the flow at the leading edge. But that's pretty dangerous stall, because if the leading edge stalls out, the entire surface stalls out all of a sudden. This is a characteristic of the leading edge stall. And then this is a very rapid loss of the lift at the post-stall behavior. It's pretty rough. You're going to all of a sudden lose entire lift almost. Strong pitch down moment, and then loss of lift once you pass the stall. So basically, airplane behaves like really jerky and very sensitive. It's difficult to fly kind of airplane. Okay. So that's the general, not always, but the general characteristics of when you choose the thin airfoil, this is going to happen. Okay. So let's move on to the next page. So next page is a thick airfoil. Sometimes thick airfoil is desired for certain purpose of airplanes, such as if you design an airplane, fly slowly, not the fastest speed, you want to make it easy to fly. Thick airfoil behaves like this. So this is going to alpha 5 degrees, CL 0.6, 10 degrees, 1.2, then you go to 15 degrees. What happens is you begin to create the circulation region near the trailing edge. You begin to induce the separation around here. So thick airfoil has a tendency to start separating the flow starting from trailing edge. So this is called trailing edge stall. So as you pitch up and pitch up and pitch up airplane, your airplane begin to become stagnant and then kind of hesitate to pitch up, because you begin to induce the trailing edge separation, and this separated region begin to grow and grow and grow. And then if you pitch really 22.5 degrees, this is probably pretty much stall region, but you still sustain some amount of lift. You have a massively separated flow recirculation region here, but you still have some attachment. So the airplane shows the tendency of stall. Your airplane actually tells you, okay, I'm about ready to stall, I'm going to stall, I'm going to stall, I'm going to stop it kind of tendency. So it's very nice response in terms of control and then pilot's controllability. This is easier to fly here. So sometimes thick airfoil is desired for certain low-speed airplanes. Now, thin airfoil, obviously, you probably want to choose the thin airfoil for fast-end airplane, which is quick response and quick maneuver, high CL max, but again, it's going to be fairly sensitive, jerky airplane to fly. Okay. So this is just a sneak preview of what the real field looks like. And then using thin airfoil theory and vortex method, we can, of course, represent to a certain extent, we can analyze the full field. Okay, so that's the fundamental concept and then purpose of this unit C3 and unit C4, and then purpose of the project also. Okay, I hope you get the concept out of C3 C4.